Let's talk about atmospheric CO2 and atmospheric pollutants, especially as derived from natural sources. Okay, so let's start with this. So when we think about the atmosphere, it's easy to lose sight of what a small fraction of the atmosphere is actually comprised by carbon dioxide. So if you look at this, nitrogen constitutes about 78% of the atmosphere, and this is true from the bottom to the top. Oxygen about 21%, and carbon dioxide, it is just this little tiny amount. It's 0.04%, and I mean that's percent, right? So that's not 0.78 there. That's 78. That's 0.04. It's a tiny amount, but it's so important in the role it plays in moderating the temperature of our planet's surface. Now, let's just talk about some of the natural sources from it. So, respiration. So, the respiration of any organism. So, we're talking mammals, fish, bacteria, molds, trees, soil organisms, bacterium, everything on the planet, with very few exceptions, anaerobes, but everything else, respiration puts carbon dioxide into the atmosphere. That includes decomposers like mushrooms and fungi and maggots and all the disgusting things that decompose organisms when they die. Uh, Basically, decomposition is just the slow process of being consumed, and that means the things that are consuming are going to produce carbon dioxide as they respire. Respiration is a product of the chemical process by which energy is extracted from carbon compounds. Now, there's other non-biological sources. So, volcanic activity is a main one. So, when volcanoes erupt, this explosive force with which they eject material upwards, in order to do that, you have to have gases. And the gases that are generally pushing the material upward in a volcano is mostly water vapor, carbon dioxide, sulfur dioxide. Those are the main gases that are present in volcanoes that push things upward. So carbon dioxide is a fairly significant component of this. And where does it come from? Well, limestones, which we had when we did the lab with the acid dripping through the sand. Limestones have calcium carbonate in them, and that means CaCO3. So during subduction, that limestone goes down into the mantle and melts, and the calcium carbonate, as it melts, liberates carbon dioxide into the magmas that then come up in volcanic activity. Okay, now a really important source of carbon dioxide in our atmosphere is actually the ocean. So gases dissolve into liquids. And if you remember from chemistry class, whereas solids like sugar dissolve more in warm liquids. So if you have a hot water, you can dissolve more sugar into it. But the opposite is true of gases. So when you have a hot liquid, it's like water. It's difficult to get gases to dissolve into. So when you heat up a liquid, gases leave the liquid. So what happens is near the polar regions where water is cold, carbon dioxide will diffuse into the water. But when water reaches the equator or the tropical areas and warms up, carbon dioxide leaves it. So there is this interplay of carbon dioxide going into the ocean when the water is cold and out of the ocean when the water is warm. Another source of carbon dioxide would be combustion. And so combustion always produces, like respiration, CO2 plus H2O. So forest fires are a fairly significant source of carbon dioxide in the atmosphere. Now let's talk about particulate matter. Not just carbon dioxide, but we also want to focus in on particulate matter. So this is a beautiful photograph here. So volcanoes are a major source of natural PM 2.5 and PM 10. And that's because when they erupt, there's lots of different sized particles, but some of them are very, very fine particles. Some of these are silica materials, like little glass particles that are super tiny. And we call this volcanic ash. Volcanic ash comes in a variety of sizes, but some of the sizes are PM 2.5, PM 10, as well as there's droplets of SO2 and other sulfur oxide compounds. And these things often in a large eruption can be pushed all the way up. This is a cool one because you can see it's hit the troposphere here. This is flattening out at the top of the troposphere, the tropopause. But this will often blast right through there and it'll get pushed all the way up into the stratosphere where it will encircle the Earth. And this particulate matter, it reflects sunlight and it causes the Earth to get colder. So it has been well demonstrated that after large eruptions like Krakatoa and Pinatubo, um, there's been a cooling of the Earth afterwards as less light energy reaches the Earth's surface. Another source of PM 2.5 and PM10 is forest fires. So when fires burn, that smoke makes all kinds of ash and different kinds of liquid droplets. Some of these are sulfur dioxides, nitrogen dioxides, and they can be quite uh, deadly. I mean, there's a picture of San Francisco from earlier this year, and it was these weird pictures of this orange-colored skies in California. It's just because this is a lot of particulate matter here, and the small parts take a long time to come out of the air. Another natural source of particulate matter is the oceans. So when the wind blows the waves, water goes into the air, and as that water evaporates, little crystals of salt. So you get little crystals of sodium chloride, calcium chloride, calcium bromide, just all these little tiny salt crystals in the air, but mostly sodium chloride. And these can be very small. They can be in the PM 2.5 range. But I think one of the most important ones is dust storms. So desert areas, when winds blow across desert areas, the finer parts of the soils will be lifted into the air. It's like the sand will be blowing. I don't know if you've ever been on a beach when the sand is blowing or the wind is blowing really hard and the sand is hitting your legs. It kind of hurts, right? But the finer particles, the silt particles, and the mud particles, and some of these are very fine. So that some of these mud particles are in that 2.5 PM 2.5 range. They get lofted upwards, and they can be carried long distances. And so basically, when winds blow across desert soils, they pick up the finer particulate matters and they carry them quite long distances. In fact, here in Korea, we have this famous yellow dust that we get in the springtime. So yellow dust is just the product of dust storms in Central Asia. So the Gobi Desert and other desert areas in Mongolia and central China, you can see here the wind blowing across is picking up this dust from these areas here and is carrying it long distances, and it will eventually sweep across our peninsula and out to sea. And so when it blankets Korea, it's a real problem. Now, this is like noticed by the Shilla Kingdom, in the year 200. There was historic accounts of these storms happening. So they're nothing new, but there's a couple things we should know. One is that they are now carrying things today that they didn't carry before, namely heavy metals, which are released by industrial practices here. So when you burn coal to make electricity for factories and urban use, it liberates, among other things, lead, arsenic, and these particles of lead, arsenic, cadmium, they land in the soils and they get blown with the soil. So the yellow dust we're getting today, in addition to being unhealthy to breathe in these dust particles also contain very tiny pieces of heavy metal which get into our blood system, and they're quite detrimental to our health. But it's not all bad. One thing about dust storms is they carry nutrients. And so there's been a lot of interesting studies done recently showing that dust storms in the trade wind areas of Africa carry dust particles from the Sahara region fall all the way across the Atlantic Ocean. And as these drop into the ocean, they bring nutrients to this photic zone that is often very low in nutrients. And it turns out it's a very important part of the ocean ecosystem, that it allows for productivity that otherwise wouldn't exist. In fact, they're finding that the Amazon rainforest, remember, those tropical rainforest soils are not very productive. I shouldn't say they're not productive. They're not very rich in nutrients, and some of their nutrients are actually coming to them courtesy of these winds blowing these dusts across from Africa. Now let's talk about anthropogenic sources of carbon dioxide. Now it's going to get kind of depressing. Okay, so CO2 is a consequence of burning fossil fuels, period. But where does most of the CO2 come from? Well, mostly it comes from burning coal in order to make electricity. That is a very major source of, also from driving cars, but burning coal is a big source of it. Now, when you look at a coal burning power plant, you'll notice these towers, they look like what you'd see at a nuclear power plant. That's because of the exact same things used at a nuclear power plant. They're full of water and it's evaporating. So you see this steam coming out of them. This is not pollution here. This is water vapor. This is pollution. These tall stacks here, these are the smokestacks that are releasing particulate matter and sulfur dioxides and carbon dioxide and other things. So today we're just mostly going to focus on the fact that this is releasing carbon dioxide into the atmosphere. All right, let's just go quickly through how it is that these stations work. So you bring in coal. This is called a hopper. You put it in and into a boiler. So you're, and this is kind of stylish, but you're burning the coal here, and it's basically coal is just carbon. Carbon reacts with oxygen to form CO2, and basically they're using it to heat water in these pipes. So when we heat water in these pipes, it comes out as steam, and the steam blows across this propeller-like device called a turbine, and the turbine spins, and the spinning of this turbine then spins a magnet, or rather a coil of wire inside a magnet, which is called a generator, and then that produces the electricity, which we then send out to people's houses. But now I've got the steam comes in here. I've got to cool it back down. So I put it into a condenser. So now what I have is, as it comes in here, I want to bring in cold water. So they usually build these things near a river, and we pump it into these towers, and we take the water from the bottom of the tower, we put it through here, and we cycle it through here. So this water comes in cold, it picks up heat from the steam, and when it comes back out as warmer, which is why you see all this what looks like smoke, but it's really steam coming out of here. But the net effect is to have taken the heat out of the steam, turn it back into a liquid, which you can then put in here and reboil it to a steam. But burning coal produces carbon dioxide. Let me try to move my face out of the way here. Here we go. Here we are. So O2 comes in. It reacts with coal, which is just carbon, with other pollutants like sulfur and lead and other things, and you get carbon dioxide. All right, that's not my best artwork ever. But consider this: last year, the world burned 9 billion tons of of coal, and they produce in the process 24 billion tons of carbon dioxide. We're addicted to this stuff, and we produce a lot of 24 billion tons of CO2 is a significant amount of CO2 in an atmosphere that's only 0.04% carbon dioxide. So this is not an insignificant amount of carbon dioxide, given how little of a percentage it makes in our atmosphere. Now, in addition, let me move my face away from here. I better move myself back over here. So in addition to producing CO2, it also produces SO2, which is responsible for acid rain. Some of that comes out as particulate form, as PM2.5. But there's also a number of heavy elements. Lead, mercury, and arsenic are among the most important ones. And these have a tendency to bioaccumulate when they get into the ecosystems downwind from these places. So coal, it's got some serious problems, and we use a lot of it on the planet. We're completely addicted to it. We this is what Robert Fulton started burning in the 1800s, and we still haven't really changed in any significant way from that. I don't know what just happened to me there. Okay. One of the things about coal, too, is this. Like, it doesn't all burn. So afterwards, you have this residual stuff called coal ash, and you got to do something with it. So basically, at the bottom here, right, you got this doesn't all burn. So you just have this tons of it. So like, they gradually release it into the nearby water. But the bottom line is this is the single greatest source of industrial waste on our planet is this stuff called coal ash. Now, there are other sources of CO2 other than just coal. So, coal, you can tell I'm not a big fan of coal, but there are other problems too. So, basically, any vehicle that you can think of, anything that's going to move from point A to point B, almost invariably is, unless it's electrical, unless it's got like things going up, touching wires like you sometimes see on trains. Okay, if it doesn't have that, it's using an internal combustion engine to burn either liquid or gaseous hydrocarbon, an oil product. So gasoline, jet fuel, diesel, LPG, CNG, something like that. So basically, whoops, don't want that to happen. No, come back. Okay. So we're talking, planes, trains, ships, cars burn gasoline, Boats burn diesel, so do trains, jet fuel. It's all the same stuff. And it uses a thing called an internal combustion engine. I just think it's worth taking a look at what an internal combustion engine looks like and what it does. Okay. So the bottom line of an internal combustion engine is this: you have this cylinder, metal cylinder, and you have this moving piece of metal, right? And this is called a piston. And when the piston goes down, it turns this crankshaft, okay? And so this piston is just going to go up and down, up and down. And in doing so, you can see it over here. As it goes up and down, it moves this camshaft around, all right? And then this is then used to drive the vehicle, to move the vehicle. Now, so basically what happens is we bring in fuel and oxygen, and when we get just the right mix, we compress it with this, and when we get just the right mixture at the maximum compression, a spark ignites it, causing an explosion, which pushes this downward. So you can see that pretty well here. So as this goes down, you can see we're bringing in fuel, we're bringing in oxygen, and when we come up, that's when it explodes at that. So it's basically called a four-stroke. First, we bring it in, then we get our air in, and then we compress it, and then we ignite it with what's called a spark plug. Now, this produces carbon dioxide and water. It also produces particulate matter and carbon monoxide, what have you. But also, it's pretty inefficient. I mean, this system here gets really hot. If you've ever touched a car engine, it's really hot. So this is kind of a wasteful way of extracting energy from this fuel, but it's what we've been doing for over 100 years. And again, we should probably try to find a better way of doing this. Now, the reaction is basically this: octane, which is sort of the ideal component of gasoline, reacts with oxygen to produce CO2 plus H2O. Well, all right, let's go ahead and balance this. 2 molecules of octane react with 25 molecules of oxygen, producing 16 molecules of CO2 and 18 molecules of water. In other words, 2 molecules of gasoline produce 16 molecules of carbon dioxide. If you do the stoichiometry, what you find is that basically what happens is every kilogram of this you burn makes 3 kilograms of CO2. So if you pump 5 kilograms of gasoline into your car, you're going to put 15 kilograms of CO2 into the atmosphere. There's no avoiding it. Now you might say, yes, there is, Mr. Simpson. I'll get myself an electric car. And then I can just hold my head up high and say, I'm not the one making the world so bad. I applaud you for using an electric car, but you're not helping the world as much as you might think. Okay, you are helping. All right, let's be straight up about that, but not as much as you think. Here's why. Yes, it's true. There's nothing coming out the back of this car. It's just a battery. I just charge up a battery and use it. But where does this electricity come from? From burning coal. So yeah, you're not putting carbon dioxide and nitrogen dioxides into my city, in the air of my city, but you're still polluting the countryside. You're still putting carbon dioxide in the atmosphere. You're still putting sulfur dioxide in the atmosphere. You're making acid rain. You're making carbon dioxide. But it's less. Okay, so it's more energy efficient because this doesn't get hot like an internal combustion engine. But still, you be very clear: electric cars are still putting carbon dioxide in the air, just not locally. Now let's just talk about this, and we're going to study this later on its own right later in the year. But it's worth, since we're talking about carbon dioxide in the atmosphere, let's just look at this. If you look at the amount of carbon dioxide, the amount of tons, the billions of tons that we put. So back in 1998, when my younger child was born, we were putting less than 25 billion tons of CO2 in the atmosphere. And it's just gone up steadily year after year after year after year, especially when Asian countries like China and India have become more developed and industrialized, to we're now around 36 billion tons. So that's a significant change. It's like a 25% change almost just in a couple decades. And so we're not slowing down, we're increasing, we're putting more and more carbon dioxide in the atmosphere with each passing year. This graph here, every time I look at this, I'm like, wow. I mean, that tells you everything you need to know. This is the amount of carbon dioxide in the atmosphere. Now, when I first started teaching, shortly after I started teaching, we came up with these vernier probes, and one of them we have in our room right now is a CO2 probe. And I would make a point with my students like, oh, let's just see how much you're respiring. Look, the carbon dioxide level when you came in was low, and now it's higher. Well, we started out back in the 90s, I would turn on the probe and it would be like in here, like around 340, 350. Now I turn on, it's closer to 400. Why? Because every year the CO2 in the atmosphere has increased by about 1.6 part per million. So that means in 1960, we had about 310 ppm, and now we have about 417 ppm. We are changing the composition of the atmosphere. Now, it's kind of interesting. This is the black is a trend line. The red is the actual day to day. And notice how it goes up and then it goes down, it goes up and then it goes down. If you think about this, it makes sense. This is from a monitoring station in the middle of the Pacific Ocean on the top of volcano Mauna Loa. Now, it's in the northern hemisphere. What we find is these high parts are in the winter and the low parts are in the summer. Ask yourself, why would that be? What's different between summer and winter? And it's not temperature, it's productivity. Productivity is high in the summer, so plants are taking carbon dioxide out of the atmosphere to build themselves. And then the winter, there's mostly respiration occurring, so the carbon dioxide level goes up. Kind of cool. But if we look at a graph of actual temperature of our planet, and that's a difficult thing to measure, we'll talk about it later, but if we just look at the average temperature of the planet, what we see is, from the 1900s to the say 40s, it didn't really change much. But then what happens after World War II, America industrialized in a big way, and then other countries did too. And what happened? We started increasing the amount of carbon dioxide, and then the temperature followed. And we're going to talk about why later. We're not going to focus on this right now, but just for now, let's just say carbon dioxide causes global warming. Why? The mechanism we'll deal with later, but that is a reality that we got to deal with. This trend is a consequence of this trend. And this is just a consequence of industrialization, burning coal and using gasoline. Now, just want to bring this all back together. So it turns out that increasing the temperature of the atmosphere through global warming by us adding carbon to the atmosphere is causing the amount of CO2 from natural causes to go up. Now, remember, these natural causes are like the oceans and forest fires. Well, think about this. Remember that when the water gets warmer, it releases more carbon dioxide. Well, guess what? By us putting carbon dioxide in the atmosphere, essentially taking it out of here, burning it, putting it in the atmosphere, we're making the world warmer. When we make the world warmer, the ocean gets warmer. What happens when the ocean gets warmer? It releases more CO2, which makes the world warmer. Oh, man. But wait, there's more, because as the atmosphere gets warmer, warm air can hold more water, meaning that forests can let go of more water. Basically, think of it like dry air is like a sponge. It can hold more, right? So water leaves the plants. And so the plants dry out. Obviously, warm air dries out plants. Well, what happens when plants dry out? You get forest fires like what we had this summer. Governor Gary Newsom of California was saying, look, what happened in my state this summer is a consequence of global warming. And he's right. Of course, it was also La Nina. But it's just if you heat the air, it can hold more water and it makes things dry out. That makes more CO2. It also makes more PM 2.5. But for right now, let's just focus on the CO2. Well, what else happens is this. So if you increase the temperature of the air, it dries out. Well, that makes forests expand. I'm not forests. I'm sorry, deserts expand. Areas that were forest become desert. Now you have more soil exposed to these winds, so the PM 2.5 goes up in the air. So we're getting worse. The reason we're getting worse yellow dust now than we used to get is because global warming is making the deserts of Central Asia larger, exposing more soil to desertification, and therefore the windstorms carry more of it towards us in the springtime. But let's go back to the CO2 because we're going to wrap this up now. This is a classic example of what we call a positive feedback loop. And you should be familiar with this for the test. Okay, a positive feedback loop is basically anytime the outcome of an interaction makes that interaction happen either faster or more likely to occur. So look at here. So as the temperature goes up, more CO2 goes into the air. When there's more CO2 in the air, then as CO2 goes up, that causes the temperature to go up. But if the temperature goes up, it causes more CO2 to go into the air from the oceans and from forest fires and things like that. Well, then what happens is that now there's more of this. Now the CO2 gets bigger. That makes the temperature hotter, which makes even more CO2 comes out. And this just keeps going and going and going. It's called a positive feedback loop. And it's a pretty freaking scary thing. And so one of the biggest tasks that your generation is facing is how to break this cycle. This positive feedback loop must be stopped. And that's something we'll talk about later in the year. But that's CO2 for you. Thanks for watching. I know this was a long one. I appreciate it.